right, good morning, everyone. My name is Wencai Zhang, working as associate professor at Virginia Tech. I'm also a PE in mining and minerals engineering, registered in Virginia. So produced water actually is not unfamiliar actually to almost all of us here. We started working on produced water almost 3 years ago. And then actually at the beginning, we focused on direct lithium extraction from produced water. And 2 years ago, we got a project from DOE, and the project was started last year in collaboration with a professor from North Carolina State University and also Austin Elements, a startup company working on battery recycling. So produced water actually, it has many characteristics. The first one is it has a very large volume. For every barrel of oil, you may need to generate around 3 to 5 barrels of produced water. And also it has a characteristic of a very complex matrix. So basically it contains a lot of organics, and also it contains a very high TDS, a very high salinity. And right now actually most produced water is directly be used for support the production. So basically when the produced water comes to the surface, and the oil and gas companies are going to send the produced water to some other wells that need more water to support the production. And oil and gas companies, they also treat the produced water for other purposes. For example, generate clean water, but that's pretty rare. Yeah. And as far as I know, for example, for the Marcellus Sea, there is a gas company actually. Sometimes they borrow some water from the coal mines of acid drainage actually to support their production here. So basically, based on my conversation with the oil and gas companies, they do not want to take the water away. But what you can do is that you can recover the valuable components from produced water. And there are some challenges. The first one is the low concentration of critical minerals in produced water. And then the second is the complex matrix. So this makes it very difficult actually to achieve economically viable extraction of critical minerals from produced water here. For almost all the secondary resources, I think this challenge always occurs here. I think in order actually to address the issue is we need to develop comprehensive value chain. So this actually echoes Dr. Doug Weeks about oil refinery tree. So for this kind of secondary resources, we need to think about how to maximize the utilization of different components exist in the secondary feedstocks. So in this project, actually, we focus on many different aspects. We focus on rare earth recovery, we focus on carbon mineralization, and we also focus on clean water production and also lithium recovery to maximize the utilization of all the valuable components in produced water. So this is a sample we collected actually from Marcellus Sea. As you can see, it contains a lot of lithium. The lithium is 80 ppm, and it's pretty high to me for produced water. It also contains some REs, and the sample we collected has around 3 ppm of RE. And also it varies from well to well, and also from geographical to geographical. Yeah. And also it contains some strontium and barium. The concentration is also pretty high. And then actually the produced water contains a lot of calcium and magnesium, and which means actually it has high carbon fixation potential. And also it has some contaminants. The major contaminant is sodium. You can check the concentration here. The sodium concentration is almost 100 ppm, which is very high. And the good news is the iron aluminum concentration is pretty low compared with acid membrane generated from coal mines and copper mines. Yeah, the iron and the aluminum concentration is pretty low. So for the REs, actually, unfortunately, there is a lot of lanthanum and cerium, but it also contains a certain amount of neodymium and praseodymium, so which means it can be used to support the magnet production here. So technically, actually, this is a process as we used to maximize the valuable components recovery from produced water. As you can see, we have 4 technical components. The first one is RE recovery. I call it RE precipitation here. The second one is carbon mineralization, and the third one is carbonate precipitation. Carbonate precipitation is the same as carbon mineralization, but I use a different name here because they serve for different purposes. And then is advanced soil injection for lithium recovery. I want to talk about the RE state precipitation first here. So this technology was originally developed for RE recovery from acid coal mine drainage here. This is what we developed actually when I was a postdoc at the University of Kentucky. And then actually, this process, as we use this process, first time generate a rare earth oxide mix from acid coal mine drainage, with very high purity. The purity almost 98% pure. Yeah. As the technology is very simple. So basically, you collect the precipitate formed in a certain pH range. For example, for REs, you can collect the precipitate formed in the pH range of 5 to 9. You are going to get RE preconcentrate, and then you can redissolve it. What you achieve here is that you can get almost 1,000 times of enrichment in the RE concentration here. So you can increase from a few ppm to over 1 gram per liter, and then actually you can do very simple oxalic acid precipitation. You are able to generate your high purity rare earth mix product here. So we also tested this technology for produced water. We found it works actually. So basically, we evaluate the different pH values, and we found at pH 8 you can get almost 80 or 90% of RE precipitation. And if you further increase the pH value, you are going to get a lot of contaminates precipitate. So we determined pH 8 is the optimal pH range. Yeah. And then actually, after we get a pre-concentrate, actually, what we did is that we redissolve it, and then actually we do the solvent injection. We can generate actually a solution with almost 400 ppm of REs. And if you check the concentration ranges here, for example, this is the RE concentration in the redissolved solution, and in the redissolved solution, the RE concentration is only 39 ppm, but after solvent extraction, it can go up to 380 ppm. For iron, actually, in the redissolved solution, the concentration is almost 10,000 ppm, but after solvent injection, actually, it only goes up to 1,700 ppm. Yeah, so which is not as concentrated as RE during the process. So this is for RE. So I want to talk about the strontium and barium. So after actually pH 8, as you can see here, you can take out RE from the produced water. And then actually what you can do is that you can further increase the pH value, and we evaluate and then actually to 12.5. And then what you can get is that you can get magnesium hydroxide and calcium hydroxide precipitate. And then actually you have strontium and barium remain in the solution here. So and then actually you can work on strontium and barium recovery from the remaining solution here. So what we did is that, so after reaching pH 12.5, actually we inject CO2 into a solution here. And then actually we got a product, actually a crude product of strontium carbonate and barium carbonate. The purity actually is about 68% here. So the major contaminants is still calcium and magnesium. But again, actually we achieve a crude product, which means actually it needs to be refined actually to generate a high purity product here. So after strontium and barium recovery, we still have the solution, right? The solution contains a lot of lithium. As you can see here, it contains around 80 ppm of lithium, and also the major contaminants here is sodium. And as you can compare, actually the sodium level is increased compared with original produced water because we add a lot of base during the earlier steps of the process. And I want to highlight here, the lithium concentration is only 80 ppm, but the sodium concentration is 90 gram per liter, which is much higher compared with lithium. So what we did is that we use solvent injection, and we use a synergistic extracting system. As you can see, actually the D here means the distribution ratio, which means affinity of the extracting towards lithium. And as you can see, when I use the two extracting separately, the distribution ratio is almost 0, which means you do not have any extraction capability for lithium. But if you mix them, then yes, you can get a very high distribution ratio, which means they have some synergistic function actually for lithium extraction here. And then actually the solvent injection contains 3 steps: the extraction, the scrubbing, and the stripping here. In the extraction, actually you can get lithium and some contaminants go to organic phase. And then actually in the scrubbing step, actually you selectively get some contaminants out from the organic phase. And in the stripping step, actually you can remove lithium completely from the organic phase, and you get a stripping solution that contains almost only lithium. So after we get the stripping solution, we do carbonated precipitation, and we got a product actually which qualify battery grade, which is 99.5% pure. Okay. And after lithium recovery, as you remember, actually we generate magnesium hydroxide and calcium hydroxide precipitate here. So we use those hydroxides actually for carbon mineralization, and we determine the optimal conditions at pH pH values. We also evaluate the phase transformation during the reaction process. Okay, so what we can get here is here. We do a preliminary mass balance for the produced water flow sheet. And as you can see here, from 1 ton of produced water, we can get around 30 kilograms of CO2 fix, plus 10.5 kg of crude barium carbonate and strontium carbonate. We can also get around 0.34 kilogram of lithium carbonate. And we can also get around 6 liters of RE enriched solution. So this is what we can get using this process. If you check the recovery here, we can find some solutions. For example, the lithium recovery here is only 80% because a lot of lithium is lost during the scrubbing process of soil injection. So in the continuous operation, what we can do is that we can recirculate the scrubbing solution to the extraction stage. In this case, actually, you will minimize the loss of lithium actually to the scrubbing solution here. So overall, this is just batch scale testing. I think we can get better results as well if we do some continuous testing. We also did some preliminary techno-economic analysis. I would say this is very preliminary, and I just talked with my graduate student yesterday. Some data, I don't trust that yet, so I argue with the students here. But this is very preliminary. I think what we can do is that we can check the inputs, the consumptions of chemicals in this process. The most of the consumptions is sodium hydroxide, hydrochloric acid, and also ascorbic acid here. And also for the extracting, actually, it's reusable, so we do not count the consumption of the extracting there. For the ascorbic acid, I want to mention here, the function it used actually in the soil injection of RE. If you are working on RE separation, actually RE separation is difficult, but if you want to separate RE from ferric ions, it's also very challenging because most extracting has a very strong affinity for ferric ions here. So that's the reason why we need to add ascorbic acid to reduce ferric ions to ferrous ions. So that's the reason why we add ascorbic acid here. But actually, we have some other technologies to address this issue. For example, if you check this figure, so this is a synthetic solution, and we add hydrogen peroxide actually to convert ferrous ions to ferric ions. Make sure actually iron stays as 3+ ions in the solution. And then actually we do some separation. We found that actually we can selectively separate ferric ions from the neodymium, which means this can be quite useful actually to get rid of ascorbic acid actually in this process. So this is a summary. As I mentioned, actually, this process is just developed based on batch testing, and hopefully, actually, over the next 2 years of this project, we are going to do some parallel testing or benchtop continuous testing. And then actually we can refine the operator parameters, and also maybe the economic data will become better. Yeah. So acknowledgement, so this project is funded by DOE, and our lab received several fundings from a project from DOE, including actually the projects from Dr. Doug Weeks here. And also I want to acknowledge Marek and his team actually to get this workshop organized. And advertisement with the permission from Marek here. So next week actually we will have a ACS 4 meeting. We will have a symposium focused on critical mineral recovery and also characterization. We have 3 technical sections, and we have almost 40 our participants. I think this will be a very great discussion about the technologies associated with critical minerals. Okay. So that's the end of my presentation, and thank you very much. Yeah, welcome if you have any questions. Yeah, thank you.